Okay guys, we're gonna start on this section with defining the trigonometric functions of any angle now. So we're gonna extend our knowledge from the previous section. We've seen how to define the trig functions as ratios of the right triangle, the size of the right triangle. We only find the trig functions for those acute angles, which are angles between 0 and 90 degrees, right? Or in radians 0 to pi half. So how do we find the same trig functions to any angle now? Positive, negative, more than 360, more than 90 degrees, more than 360 degrees. So that's what we're gonna do here in this section. The idea is gonna come pretty much straight from what we've already done, the right triangle. So let's say I have the first quadrant here and I have a ray here. I'm gonna have an angle right here. So right there, let's say that's angle theta. Okay. And then we're going to drop a perpendicular here. So again, this is standard position. This will work actually on any quadrant. I'm just choosing the first quadrant to make it simple here. So if we drop a perpendicular right here to our x-axis here, so then we have now, and let's assume we have this point right here is x comma y. Right, so we have our point x comma y. So then if we drop a perpendicular here, this would be x right there. And this right here would be y. So it's just an arbitrary x comma y. So let's assume we have a point x comma y there, right on our terminal side. Our x coordinate, y coordinate in this way. So I form a right triangle here by dropping a perpendicular, and we have our angle theta there. So because the vertex here of this angle is the origin, so then we know that this right here, this side right here, that is x right there. In the same way, this is y. So then if I let this be some r, the length of this ray be r, based on our right triangle trigonometry we saw in the previous section, we can define the 6 trigonometric functions of this angle theta. So here they are, guys. We have the 6 trigonometric functions defined with our x and y here, and this length of the ray that we call r. Notice how everything is the same from our right triangle trigonometry. I mean, we're deriving these from the right triangle. We're just having to place it on the first quadrant here, and we're noticing how our opposite and our adjacent side are x and y, which are the coordinates of this point here that it happens to be on the terminal side. Now r is just going to be the length of the ray, and now be careful here. So for some of these you want to make sure x and y are not 0, otherwise they'll be undefined, right, for some of these. And then obviously r here is not going to be 0. So how are we going to find r? For us, r is equal to the square root x squared plus y squared, and this would always be greater than 0. Technically it's greater than equal to 0, but for our purposes, I mean, the only way it would be 0 is if you're right at the origin and then you don't have an angle then, right? So, or you don't have a ray. So this ray, because we're talking about length here, this ray will always have to be positive. So then, you always guarantee to have a positive here. So we can assume for our purposes that it will always be positive. So in other words, greater than or equal, not the equal, but just greater. So then this is how you find r. It's basically just a distance formula here, if you remember that. If not, here's the formula on how to find r. Once you have r, this point will usually be given to you, so then you can derive all the 6 trigonometric functions for any given angle. Now again, guys, this definition is going to work anywhere. You just need that point, some point on the terminal side. So this will be the definition for any angle now. This would allow us to find trig functions of any angle because I can be on any quadrant. I can go around as many times as I want on either direction. And this works for positive and negative angles. So let's do an example here. We have a point on the terminal side of theta, and here's our angle theta. That's going to be in our second quadrant here. And we're asked to find all the 6 trig functions of theta. So again, using our definition here that we just discussed, we no longer have to keep doing the right triangle. Now, before we can find all the trig functions, we need to find what this r is, right? So first thing we want to do is just compute r. So r is going to be the square root of, and it's right here, x squared plus y squared. X for us is -5, and y squared is 12 squared, which is equal to the square root of 169, and that comes out to be a nice 13. Right? So once we have our r, we're ready to find our trig functions. Right, so here they are, guys. Again, it's just from the definition here. We're using our order pair here and the r that we found to come up with the trig functions and whatnot. So this allows us to find now the trig functions of any angle here, no matter where they land, what quadrant, right? So, oh, something I forgot here is, even though the ratios are the same, notice how -5, the x coordinate is negative, so we need to add those negative. We're gonna have some answers here negative, so the negative would be here. So out of the 6 here, we end up with 4 of these answers are negative, and the 2 sine and cosecant still positive. So hopefully you'll start seeing here a pattern, and we're going to generalize this and make sure that you see when certain trig functions are positive, when are they negative, and that will depend on what quadrant we're in. Okay, so notice how we have our 4 quadrants here, and everything is positive here. So in terms of the coordinates x and y, you have that x is positive here, and then the y is also positive. We can do it in the same way for the other 3 quadrants. So x is negative here, y is positive. Both x and y are negative, and then we have that x is positive here, but the y is negative on the 4th quadrant, right? So another way of representing the quadrants are with these intervals here. So we know the first quadrant goes from 0 to pi halves. So data between 0 and pi halves, and I'm staying in radians here. So that we can start getting used to the radians. The second quadrant would be pi halves, from pi halves to pi. Right? Then we have from pi to 3 pi halves, and then 3 pi halves to 2 pi. Okay, so it's another way of representing the quadrants here. And notice how these don't have the equal. It's because this what we call quadrantal angles are not part of the quadrant. So when we talk about quadrants, it's everything within those axes, right? Now from here, based on the sign of x and y, we can come up with our the signs for the trig functions that we've defined. So on the first quadrant, obviously both x and y are positive, so that's going to make everything positive here. All trig functions are positive. So I'm only going to, they're either going to be positive or negative. So I'm going to either just put the positives here so that you assume there's only 6 trig functions. So if they're not in here, they're not positive, then they'll be negative. So in the second quadrant, as we saw in the previous example, only sine and cosecant are positive, right? So then you'll say sine, cosecant, and that makes sense because they're reciprocal of each other, are positive. On the third quadrant, it's going to be tangent and cotangent. It's always the trig function with its reciprocal. And then finally, on the fourth quadrant, you're going to get cosine and secant are the ones positive. So notice how, with the exception of the first quadrant, where everything is positive here, all the 6 trig functions are positive, only 2 out of the 6 are positive on the other 3 quadrants. That's understood that the other 4 on any given quadrant will be negative. Okay. All right, guys. So we now are ready to talk about the unit circle and fill in this unit circle for that we're going to be using for the rest of the semester and moving forward too. So unit circle is just a circle with radius 1. The word unit means 1, and this is a circle with radius 1. So then we're going to start filling in some of these known angles. So what we're going to do is, and notice how for each angle here, I have there's two spaces here. One is going to be the degrees and the radians. So we're going to use both measures here so that you can compare them back and forth. And for those that are not used to radians yet, you can start getting used to these, right? Eventually we want to, for these angles here that we're going to see in the unit circle, we want to just start thinking in terms of radians here. So the first one here, right here on the positive x-axis, we have 0 radians, same thing as 0 degrees. And we can go ahead and just do this right here. We know this is 90 degrees, which is also pi halves, right? And then we have all the way over here, half a revolution would be 180 degrees, or same thing as pi. And then we have all the way here, 3/4 of the way would be the 270 degrees, or 3 pi halves. Again, if you don't know those angles right away, you can always use your conversion factor. And then we go back to the beginning, the whole revolution. That would be our 2 pi, or 360. All right. So then we have our quadrantal angles here, so right on the axis there. And we can already fill in those ordered pairs for those quadrantal angles. So remember we said this circle has radius 1. So then this point right here, this point right there, will have to be, if this is the center, this has radius 1, so then this will have to be 1,0. 1,0 there. Then we can fill this one in. This is 0,1. And we have -1, 0 now. And then the last one here would be 0, -1. All right, so that much we know, just from the fact that we have this circle have radius 1. So we can figure those out. Now our job is to fill in the rest of this circle here, and you're going to see the symmetry here. So important there that they're going to be very similar except for the sign here. Remember how we said these trig functions are going to have different signs depending on what quadrant you're in. Okay, so we start with the first quadrant here. If we get this first quadrant figured out, then the rest is going to be very similar except for the sign change. So we can see that from 0 to 90 here, right halfway we have our 45, which in radians is pi/4. And again, feel free to use your conversion if you're not sure, if you want to make sure that these are in fact the radian equivalent of 45 degrees. Same thing here. So before 45, we're going to have the 30, and then after we're going to have the 60 degrees. In radians, this is pi/6, this is pi/3. Now, the order pairs for these angles are going to come pretty much from the part where we discussed the special right triangles. So remember these special right triangles that we did on the previous section. If we go back to what we were doing here, if we drop a perpendicular for each one and start making, the right triangle to derive this formula here, remember that this is going to give us the trig functions of any angle now. So applying this definition, we can derive this order pairs here. And if you remember, going back to the lesson here, that previous lesson where we did the special right triangles, notice how we derive these right here. Okay, so now maybe a good point to rewrite this right here. Now remember, all of these rays here, all of these sides right here are length 1, because this is a unit circle, meaning it's a circle with radius 1. All of these are 1. So the r on this definition, the r is actually 1. So then all of these turn into just 1 right here for our unit circle. So then we can say then on the unit circle, sine of theta is equal to just y. Cosine of theta is equal to just x, and tangent you still have to do y over x. Now obviously the other three are reciprocal of the first three, so you can do 1 over y secant, it's 1 over x, and then cotangent is x over y. Right, so that we can just entirely drop the r, because r is 1 here in our unit circle. So this means that for any ordered pair here, x comma y, we're going to have really cosine comma sine, because the x is cosine and the y is sine. So if you think about that and go back to that previous when we did the special triangles, notice what sine of 45 is square root of 2 over 2, and cosine of 45 is also square root of 2 over 2. If you look at sine and cosine of 30 and 60, yeah, they were very similar. Remember, we talked about cofunctions. So sine of 60 is the same thing as cosine of 30, and vice versa. So we can use these now as our ordered pair, since we've already done them here, and fill the rest of our unit circle here. So we'll start with the 45. 45, that's square root of 2 over 2. Square root of 2 over 2. Now for the 30, you're going to have square root of 3 over 2 and 1/2. And then for the 60, you flip those, because remember they're complementary angles that are going to switch here. The sine is the cosine of the other one and vice versa. And this is square root of 3 over 2. And there it is. Then you have that first quadrant. You're going to see that the same pattern is going to repeat on the other 3 quadrants. There's just going to be a sign change, and we've already discussed where, which ones are positive and which ones are negative. So let's start by filling in the rest of the angles here. All right, so here are the angles with in radians and degrees. You're going to get the same point that you got here, right there. You're going to get it over there, except with the sign change. So this would be 1/2 and square root of 3 over 2, same thing, but the 1/2 would be negative, right? And every x here would be negative on the second quadrant, and so forth, right? In the third quadrant, both x and y are going to be negative. Fourth quadrant, just the y is going to be negative. So we'll fill in everything the same way. Right, there you have it, guys. So notice how all the values are the same, the quantities, except for the sign change. So you just got to remember what's negative and what's positive on each quadrant, and that's very straightforward if if you look at the x and the y. So what's important here, that because we made the circle to have radius 1, then it's easy to compute sine and cosine of any angle here, or any coterminal angle, right, to any of these, because sine just becomes y. Remember, the r is 1 here, so instead of y over r is 1, so it's really just y. Cosine is x, and tangent is still, you got to do y over x. And obviously, if you know this 3 right here, you can always flip those or reciprocate. Right, the reciprocal of those will be the other 3. So this circle here is, we're going to use a lot for just moving forward on anything. We'll use these angles or derivatives of those angles, and just about any problem we'll see from now on, and any topic that we'll go over. So make sure you practice filling in this circle there, and also make sure you know now the abbreviated form of the strict functions, now that we don't have to do with the r, since r is 1. Also make sure that these denominators here are not 0, otherwise you'll get undefined. The trig function will be undefined, but especially for sine and cosine, you're able to find quickly what the trig functions are without doing any calculation if you're asked to find one of these angles here. Like for instance, if you want to find the sine of 150 degrees, right, or 5/6, then sine, is the y coordinate. So you just look at the ordered pair here, and you look at the y coordinate of 150 degrees, and that's 1/2, and the answer is just 1/2, right? If you're asked to find cosine of 5/3, you go to 5/3 right there. Cosine is the x, which is the x coordinate, so it'll be 1/2 as well, right? It happen to be positive. Now, if you're asked to find tangent, then you still have to do the ratio y over x, but you have the y and the x for any of these angles here. So like for instance, tangent of 225 degrees, you find 225 degrees, or 5 pi over 4, and tangent is y over x. Take this y divided by that x, they happen to be the same thing, so and they're both negative, so the negatives cancel out, and then you have just 1. Tangent of 225 degrees is 1. So we're going to be doing this, a lot of this, and a lot of practice with this, and make sure we do enough exercises for you guys to practice. Okay, so here we have one more definition that I want to go over in this section, and is that of the reference angles. If we have an angle here in standard position, I have the 3 possible scenarios here. We have our angle theta here, second quadrant, you can have it on the third quadrant, and you can have it also on the fourth quadrant. Our reference angle, we'll call it theta prime, would be the angle formed by the terminal side of theta, in this case our angle here, whatever angle we have, with the horizontal axis. So for instance here, this would be your theta prime. Not this right here, not with the y-axis, but with the x-axis, or with the horizontal side. So this right here would be your theta prime, your reference angle. Then finally this. It turns out that the trig functions of the reference angle give you the trig functions of the angle in question. So that's another way of thinking about it, except for the sign change. So this is important for when you have, angles that are more than 90 degrees. Again, but with our definition up here, you should be able to do any number here. Now, so this extends to all real numbers, right? Because we can go from 0 in the positive direction, we can go to infinity, as large as we want it to be. And also from that same 0, we can go backwards, right? Go clockwise. So those angles, that definition of the trig functions for any angle extends to any real number now. And the reference angles is just giving you the idea of, okay, well, if I have this angle here, remember this came from the right triangles, so the trig functions of those reference angles match the trig functions of the angle in question here, no matter what quadrant they're in, with the exception of possibly a sign change, but the quantities are the same. Okay, a couple of things that I want to mention. One is a definition that we'll be investigating a little bit more when we graph all these functions on the next section, and is that a function is periodic when there exists a positive real number c, such that this is true. F of c, t plus c is equal to f of t for all t in the domain of f. Now we're going to see that this is true for all of these functions, and intuitively, guys, you can see this from just the unit circle. Think about how everything right here, right, like for instance 30, and let's do degrees, make it easier here. 30 degrees, sine of 30 degrees is 1/2. Remember, sine is a y. Well, if I go around one time, a full time, so 360 from this 30, I'll end up right at 390. So remember, coterminal angles here. I mean, we're basically finding a coterminal angle. So if we add 360 to 30, we get 390, but we're back at where 30 is. So if I were to find sine of 390, it would also be 1/2, because it's right here back where the 30 is. So notice how there's going to be a lot of repetition. We'll go around over and over, and we can also do this clockwise. So this is what we call a periodic. When you start repeating after a while a certain number, and you can kind of see and guess that the number here is going to be 360 degrees, in other words 2 pi. So this c, for sine anyway, sine and cosine, it will be 2 pi. So this c that they're talking about, so as long as there is a number that after that, after a while that happens, you get this equality here, then you're going to have a periodic function. Well, all of the 6 trigonometric functions happen to be periodic, And you can see, for obvious reasons, we go around the circle over and over again. So we're going to have the same values, right? We're also going to be talking about domain and range when we look at the graph of these, and you'll see we'll go into more detail there as to what the domain and range is for each one of these. Okay, and one last thing that again we'll be doing a lot more of next section is something you've done before. It's even and odd functions. Now we've defined these functions here. We're going to graph them in the next section, but we have that some of these, specifically sine and secant, cosine and secant, are even, right? So if you don't know, remember what that means. Is basically the cosine of negative t is equal to cosine of t. Same thing for secant, and the other four, sine, cosecant, tangent, and cotangent, are going to be odd. So those are going to give us some nice results. Later on we can form or come up with even and odd identities as well. So we can use this to deal with some negative signs later on. And then we'll be able to see the symmetries that happen as a result of characteristics of these functions.